All right, so when we started discussing graphs a couple weeks ago, right? So what is a graph? So let's finish up our discussion of graphs and some graph algorithms. So quick review, what is a graph?
Data structure.
It's a data structure, okay, so it's a set of what? Vertices connected by edges, okay? They can be directed or they can be directed or non-directed. What's a directed edge?
Which has direction.
Meaning, for example?
It has an arrow for an edge.
Okay, so if I have a directed edge from A to B vertex, what does it mean?
A, edge, an arrow, and B.
Yeah, what does it mean?
It's going from A to B.
I can go, I can start at A, I can go to B.
But not
What about from B to A?
No.
That edge does not allow us to do that because it's directed. Okay. If it's an undirected edge, then an edge from A to B means you can go from A to B or B to A, right? So directed, undirected. What about weighted edges and unweighted edges? What's a weighted edge?
The cost of traveling from one vertex.
So we have a cost involved, Like for example here, in this, if I look at this graph right here, I can go from A to D, right? On a directed edge, I can go from A to C on a directed edge. What's the cost? What's cheaper, go to D or to C?
C.
We don't know. We don't know, right? Because there's no numbers here. It might look like it's shorter, but maybe there's a big mountain and it takes a long time. We don't know if it's a city to city. Maybe there's delays on a network connection. Maybe there's more traffic from A to C than A to D. Who knows? So we don't know what the difference is. If we have no weights, we can make an assumption that every single edge has the same cost. So an easy way to look at it is just assume that the cost of every edge is 1. So if I'm trying to get, let's say, from A to F, I can get the A to F from 1, cost of 1, cost of 2, and cost of 3. I can also go here, cost of 1, cost of 2, cost of 3, but I can also go cost of 1, cost of 2. So in some cases, I may be able to have fewer edges. We call them sometimes hops. Hop, 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 right? Hops, we hop from vertex to vertex. We call them hops. So we may be interested in finding the shortest path. Okay? How do we find the shortest path? Well, there are two basic algorithms that we studied in the beginning on graphs, and those are called traversals of graphs. And we looked at two kinds of traversals, this type of a traversal and this type of a traversal. Remember what I'm referring to? Breadth first, so breadth means width, or depth means deep, right? So who can tell me what is a depth first traversal? What are we really doing?
Nodes to the leaves.
So for any traversal, what do we do? What's the first thing we do for any traversal? Start someplace. We start someplace, right? And then what do? We have a set of neighbors, right? And those neighbors can be represented either by an adjacency graph or an adjacency matrix or an adjacency L. List. Remember we talked about the adjacency list? Adjacency list is a list that basically talks about only the neighbors that are actually there. Oftentimes we use that for a sparse graph representation, something like that. So we have adjacency list, adjacency matrix. So let's say I am starting, let's say for the sake of argument, I'm starting at vertex A. What are all the neighbors from A? B, C, and D. Okay, so if I'm going to do a depth first traversal, I may start directly going to B. Why B? Well, if I keep them in alphabetical order, then maybe I try to go to B first. Once I go to B and I'm doing depth first, I look at the possible locations. Now I can go to C, D, or G. So I'm probably going to go to where? C by the same rule, right? And then from C, I can go to only E. So I go to E. From E, I can only F. So I go to F. From F, I can't go anywhere. Am I done? Well, if I'm doing depth first, I'm doing recursively, so that means from F I go back to see, could I go anyplace else? No. Could I have gone anyplace else? No. Could I have gone anyplace else? Yes. So I go back to here, and then I would probably try D. From D, I try to go to F, but I've already been there, so I don't go there.
G.
I can go to
G.
G, and from G I can go to E, but I've already been there. How about C? Have I been to C?
Yes.
Yes, yeah.
I have.
Oh, yes, yeah.
Yes.
A, B, C.
In the first.
For depth first? For depth first I did?
Yeah, you,
A, B, C,
A, B,
E,
C,
F.
E, F, in the first.
Okay, yeah. Okay, so I'm not going to go there. So I'm going to go back here, and at that point, where else can I go?
That's it.
Well, I can go to G, but I've already been to G. I don't know what these funny symbols are. Very interesting. All right, so we're going to try to find the shortest path. And so basically we know that depth first traversals are based on recursion. Breadth first traversals are based on what data structure? The queue. Okay. All right, so let's take a look over here. So we're going to look at an algorithm which is going to give us the shortest path of a directed graph, assuming that the cost of every single edge is the same, and then we can use an arbitrary cost, let's say cost of 1. So what we're going to have is we're going to have a few values here. So what I'm going to do is I'm going to just sketch them out on the board so you can see them as we're tracing the algorithm or describing the algorithm here. So the first thing we have is we have a DIST, which stands for distance, DIST vector. So the DIST vector looks like this, DIST, and then this vector is, when I say vector, it just means one-dimensional, like an array, you can think of it this way. And how many vertices did we have in the graph? Do you remember? I forget.
A, B, C, D, E, F,
We went up to
Yes.
G, right?
G. Yep, 7.
D, is there an E? Yeah. 6? 7? 7. So we're going to have 7 values here. So that's our DIST vector. Okay. We are going to have a start, and start is going to be the starting vertex. That's going to be just a simple value. Start A, B, C, D, E, F, G. Then we're going to have something called distance, DIST. And we're going to set that equal to 0. That's just a scalar, or a single value. Okay. Of course, we're going to have something called unvisited, and the unvisited will be a vector of unvisited nodes. So once we visit a node, we'll check off that we've been there. Next time we try to go there, we're going to say we're not going to go there, we've already been there. Why do we need to keep track of the unvisited? What happens if we don't keep track of where we've been?
Like looping.
We can go in a cycle. That would be very bad. So you will initialize the distance vector to -1. And what that means basically here, we got a -1, -1, -1, -1, -1, -1. So for every vertex we have -1. Also, we can look at the -1, and that can double also as unvisited. If it's -1, we've never been there. So we don't have to have an unvisited vector. We can just check this one if it's -1. Okay, now the first thing we're going to do, we're going to visit start and set the distance of start to 0. So let's say we decide to start at A. So let's say this is A, B, C, D, E. I only have F, but anyway. Supposed to have one more, right? I don't think it really matters. I mean, just an example. But anyway, so what I'm going to do, let's say I want to start at A. So what I'm going to do is I'm going to set the distance equal to 0, which is already 0, and I'm going to set the DIST of start, which is our starting vertex, let's say A, equal to 0. This 0 will have a significance, and the significance of this one will be, this is the distance I am away from the start. Well, that makes sense. Since A is the start in our example, then that should be a 0. If I started at E, that would have a 0 initial in it. Okay? Okay, so now what I'm going to do is I'm going to initialize a Q to contain start. Well, the Q is going to contain, basically, it's a Q, so it's going to contain A. But potentially can have other vertices in it as well. And so what I'm going to do is, now I'm going to loop. So this is now going to be actually the algorithm which is going to traverse the graph. While the destination is not visited, now question is, where are we going to? I don't know. You can pick any starting location, you can pick any ending location. I suppose it would be a good idea to pick a different one than the starting one. Otherwise, we could just terminate the algorithm pretty quickly. So let's say you want to end up going to F. I don't know. Notice that F is unvisited because it's got a -1 in it. So while the destination is not visited and the Q is not empty, it's not empty, we remove from the Q the vertex V. So V becomes equal to the starting vertex A, and the Q becomes empty, but after we go into the loop and it being not empty. So now after we remove the V from the Q, we check if the distance of V is greater than distance. True or false? What's the distance of V?
0.
It's 0. Is it greater than distance? No, because distance is 0, and this of this V is 0. So if that's true, but it's not, so we don't increase the distance, now we're going to loop. This loop takes care of an iteration for each vertex W adjacent to V. So that means we're going to look at the neighbors of A. I don't know what the neighbors of A are, but let's say the neighbors of A are, for example, B, and let's say another neighbor is, for example, C. I think in our graph was BCD, actually. But, so what's going to happen is, for each of these W's, these are W values, if this node or neighbor has not been visited, we'll set the pred of W to V. Now, pred is another important vector. So dist is an important vector, pred is another important vector. So we'll have another type of vector. So we have A, B, C, D, E, F, G. And so what we have here, if W has not been visited, has W been visited? If W, so W takes on the value of B. Has B been visited? No. So therefore, we'll set the predecessor of W to V. Well, W is B, so the predecessor of B gets the value of V, which is A. Does that make sense? So the predecessor of B is A. What does that mean? We came from the predecessor to get to B. Then we're going to visit W, and to visit B, what it really means is that you basically you get rid of that -1, and you set the dist of W, so visited gets rid of the -1, setting the dist of B to distance plus 1, which means it's going to be distance, which is 0, plus 1, so we're going to put a +1 into B, +1. And then we're going to add W into the Q. Well, that means that B is going to go into the Q. But we're not done with that loop because we have another neighbor of A, and that neighbor is C. So what happens now, W becomes C. C has not been visited, so we'll also set the predecessor of C to V. V is still A. So we get A and A here. Okay? And then we'll visit this one. We'll set the distance of C still to 0 plus 1, which is 1. So we'll put a 1 here. We'll also put a 1 here. We'll add W to the Q. That will add C to the Q. And at that point, we are done with the loop because there are only 2 W's adjacent to V. So we're out of this loop and we go to the outer loop. We notice the destination, which is F, is still unvisited. And the Q is not empty. It has 2 elements in it. So now we iterate with what we have here. We remove V from the Q. Therefore, the next value of V will be B. We will take B. Okay. Is the distance of B greater than distance? Yes. Yes. Remember, what is the dist of V? What's dist of V? Remember that? Okay. So therefore, since 1 is greater than 0, what happens is that distance itself is increasing to 1. So distance is increasing to 1. What that means is that the current vertex V is at a distance away from the start vertex. It's 1 away from the start vertex. So now any neighbors, any unvisited neighbors from B will now be 1 plus 1, 2 away from the very beginning starting point. So for each neighbor W adjacent to V, if the neighbor has not been visited, set the predecessor of that neighbor to V, which in this case, again, at this point would be B. Visit the neighbor, set the distance to distance plus 1, which will make it, at this point, 2. And then add it into the queue. And we will do so for every single neighbor of B. Okay? Once we visit all the neighbors of B, we're going to come out of the inner loop. We're going to go back out to the outer loop. If the destination still is not visited and the queue is not empty, which it's not because there's at least a C in there, possibly, and also some neighbors of B that we visited, so the queue is growing through the inner loop, we'll remove V from the queue, so that will be for sure C. What's the distance of C? 2. No. Distance of C was set in the first time we went through here, which was 1. Remember? So therefore, since the dist of C is 1, greater than, and what's distance?
1.
Also 1. So the condition is false. Therefore, distance stays the same. What does it mean? It means when C is the current value of vertex V, we are still 1 away from the very beginning of the traversal, which is A. So that means we don't increase it. So neighbors of C are just as close to the beginning of the search as neighbors of B, because B and C have the same dist value. So now we're going to visit all the neighbors of C, if they've not been visited, etc., etc. So you get the idea. So what's going to happen is we're going to fill out this distance vector. We're also going to fill out this pred, or predecessor, vector. Once we have a solution, or once we terminate the algorithm, we may not have a solution. Once we terminate the solution, then we're going to say the distance is going to equal the distance plus 1. If the destination is not visited, meaning if the dist vector has a minus 1 in the destination, then we can say destination is not reachable from the start vertex. Else, we're going to say the path vector initial position is the start, and then the path distance is equal to destination. So we'll start the beginning of the path as start, the end of the path as destination, and then we're going to fill in backwards the path vector from distance minus 1 down to 1 by putting in the predecessor, using the predecessor table. So I'll show you an example of that. So let's say we want to go from A to E. So let's look at the idea of going from A to E. So A to E, you can see there's a whole bunch of ways we can go to A to E. We can go A, B, D, G, E. We can go A, B, G, E. We can go A, C, E. That appears to be possibly the best way to go. Okay, so that's the idea. So we're going to go from A to E. And so what we're going to do is we're going to apply our algorithm, and when our algorithm is finished, or actually as our algorithm is growing, we initially will start A as the vertex, so everything else will be minus 1, and the predecessor vector is empty. The visited vector is just, again, kind of like you can see how that is. We visited this one, so therefore its distance is not negative 1. Okay, and then distance is equal to 0. Q gets a value of A, and then we go into the inner loop. And the neighbors of A are what?
B.
B, C, and D. So that means we're going to have 3 values going in here. So our W values are the neighbors, B, C, D. B is not visited, so the predecessor of B gets A. We visit B. We said distance of B equal to 1 because that's distance plus 1. Distance is 0, so plus 1 is 1. And then Q is equal to B. So we put into the queue. Now we go for the second neighbor of A, that's C. Not visited, so we set its predecessor value to A, which is still the current V value. We visited, we set the distance to distance plus 1, which is 1, and we add it in the queue. And then we go to the last neighbor of A, that's going to be D. Again, here, set the predecessor, visited, set the dist value at 1, and then the queue contains BCD. So now we're done with the inner loop. We go to the outer loop. What's at the head of the queue?
B.
B. So B is the head of the queue. We take B. Okay, that's the state of the vectors. So you can hear 0, 1, 1, 1. Notice that distance means A is 0 away from A. B, C, and D are all 1 away from A. And E, F, and G have not been visited. The visited vector has included the first 4. Anything that's not a -1 has been visited. And the predecessors are A in the case of BCD, because they are the direct successors of A. A is their predecessor. So now we take B out. Now we take B out. The queue is down 1 element. The distance increases by 1. Now we look at the neighbors of B, which are C, D, and G. C, very quick inner loop, it's already been visited. So now W goes to D, already visited. So now W goes to G. G has not been visited. Set its predecessor to B, visit G, and set the distance to the distance plus 1, which is 2, and add G into the back of the queue. Okay? So now we have C, D, and G. This is what our distance vector looks like. Notice that G is now 2 away. The predecessor here is B. And the visited vector only has two vertices that have not been visited. So now our V value is equal to C. The Q is remaining with 2 values. The distance stays because C is just as far away from A as was B. Its neighbors are E and G. Notice that E is going to be a success for us in a second. We set the predecessor of E to C. We visit E. We set the distance of E to 2, which is 1 plus 1. And we put E into the back of the queue. All right, and then we go to the neighbors of E, which are F and G. And G has already been visited. So the algorithm now terminates as E was visited. So as we check it, it terminates. And so this is the final state of the tables. So the final state of the tables, where do we try to go to? We try to go from A to E, right? So if you look at the distance to E, notice that it's going to be 2 steps. 2 steps. Okay, so if you go to E, what's the predecessor of E? C. What's the predecessor of C?
A.
And A is the starting. So that means that our path in reverse is going to be E, and before E we go to C, and before C we go to A. So A, C, E. That's our path. Okay? So the distance when we come out of the algorithm is going to be equal to 2 because dist distance has a value of 1 initially when we come out of the algorithm, and that's because when we went to E, we were at the predecessor of E, which had a distance of 1 less than E did from the start vertex. So therefore, we have to always add 1 to the distance. The path 0 is start. That means A. The path distance is going to be destination. That's going to be 2. And then this is the backwards loop. So for distance minus 1, which means it's going to be 2 minus 1, which is 1 down to 1. So it's only 1 iteration. Path sub 1 is going to be equal to the predecessor of path sub 2. So we'll go to the predecessor of E, and that predecessor is, do you remember? C. So that's going to fill in a C. So the path is going to fill in a C. And so now once we fill in this one, we're ready to go and we have the solution. Okay, any questions? So what algorithm did we use for traversing the graph?
Breadth first.
Breadth first. And the reason is because we don't want to go deep and find it and go 16, edges, right? when in fact maybe we could have gone 2 edges and found it. So we basically try to go, we go from the starting, every place we can go by 1, every place we can go by 2, every place we can go by 3. So if we do that, if we do a breadth first traversal, that means the first time we encounter a vertex will be the nearest to the starting point. So that's why it's going to be called the shortest path algorithm. Get it? Shortest path algorithm. Now, in this case, we are interested in not necessarily the shortest path, but we're interested in what? Least cost. Because sometimes the number of hops between vertices may be larger, but the overall cost may be smaller. As you know, sometimes when we take airplane flights, if we want to go directly to a destination, sometimes it's more expensive. Sometimes it's less expensive to go to 5 different hops. Oh, sure, we'll take you to Minnesota, and then back to Chicago, and then to Atlanta, and then we'll fly you to San Diego. Very cheap flight. You're going to be flying all day. Any delay is going to be a problem for you, as you know. So sometimes longer paths are actually cheaper paths. Okay, so it depends. So you can see here that this is, again, we have a digraph here, a directed graph, and you can see that it's very cheap to go from A to B. Okay, but you can see it's also very expensive, relatively speaking, to go from A to E. In fact, it appears to be the most expensive one. So what we want to do is we want to find the least cost path of a graph. So let's take a look at this graph with respect to its adjacency list. So this is an adjacency list where A has the neighbors of B, okay, and also neighbors of E and D. So we have B, D, E, and F. B, D, E, and F. But in addition to having just the neighbor of A, we also have the cost. So it's an adjacency list we just put into this node. We actually add also a cost. So we have some idea what the cost is going to be. Everybody understand the structure? Okay, so let's say I want to find out the cheapest way to go from, let's say, from F. Now, by the way, it's possible that there may not be a way to go somewhere. For example, if I want to go from F to B, can I do that? F to B. You know, I can go to A. Can I go everywhere? Looks like there's a big cycle here, right?
Yes.
Looks like there's a big cycle so fast. So basically, any node can basically go to any place else. So we're looking for the cheapest cost. It's possible, and by the way, if I back up a little bit, it's possible that here I might have tried to go with some place where there's no way of getting there. For example, if I tried to go from F to B, I would have been out of luck. Which means that the algorithm also can report that the algorithm terminates because the queue is empty. But the node of destination has not been visited, and that means that you can't get there. And so it's still a traversal algorithm. Still a traversal. Okay, so here is the algorithm that I'm going to propose for you to find the least cost. And let's see how that's going to go together. So what we're going to do is we're going to have a possible path list. Possible path list, and then we're going to have a path list. Possible path list is a path that might get us to start to destination. Which means it's not a complete path, but it's still potentially possible. When a possible path becomes not possible, it's taken off the possible path list. When we find an actual path that goes from start to destination, we put it into a path list. But we don't terminate the algorithm because we want to make sure that there are no other cheaper paths. So we want to calculate all the paths. Not the shortest, because the shortest may be the most expensive. maybe the longest, or maybe the almost longest. Maybe something in the middle will be, in fact, the cheapest, least cost. So what we're going to do is we're going to set the possible path list to a zero-cost, single node path of the destination. What does that mean? It means if I want to go to, let's say I want to end up at E, then the possible path to E ends at E with a cost of 0. It means if you want to go from E to E, there you are, cost of 0. Thank you. Thanks for flying United, right? So now, but if I'm not interested in going from E to E, but let's say I'm interested in going from C to E, then I look at all the possible ways I can get to E. I can get to E from D. If I get to E from D, is that a possible path from C to E?
Yes.
Potentially. I don't know, right? It might be. If I go from A to E, is that a potential path from C to E?
Yes.
Yes? Okay. How about if I go from F to E?
Yes.
Same thing. Okay. So what would happen is, at the second step, I would say my possible path goes from D to E with a cost of 2, A to E with a cost of 7, and then F to E with a cost of 1. And these become my possible paths. And then I go to the next step. So what I'm doing is I'm trying to get to the point of the possible path. And since it starts at E, I'm looking at how can I get to E. So now I have 3 possible paths, so for the next iteration, I'm looking at all the possible ways I can get to D. So now the possible path becomes B, D, E, A, D, E, C, A, E, and C, F, E. Notice that 2 of those possible paths are also now paths, because they're going from C to E. Once they go from C to E, they become not only possible paths, they become actual paths, and they have an actual cost, which we're going to move them from the possible path list into the path list, and we're going to keep the path list in what kind of order? In sorted order. In sorted order. Yes. Okay. So I'm going to show you what this looks like, and then we'll go through the algorithm.
Sorted on depending shortest path or low cost. Sorted on
Least cost.
Least cost.
Not shortest. We don't care about the length. Now we only care about the cost. Okay. So you can see on the first iteration that in order to go from A to E, you can go to E. If you start at E, you can go to E with a cost of 0. If you start at E, you are at E with a cost of 0. Great. Okay, and the path list is nil. I don't have any paths yet. So now what I'm going to do is I'm going to look at all the possible ways I can get to E. And if you go back in the path to get to E, notice that E has 3 incoming arcs. From A, from D, and from F. F to E is only cost of 1. A to E is a cost of 7, but it's already a path. And D to E is 2. And so what's going to happen here, this shows me that I have a path from D to E with a 2. It's a potential path because it ends at E, but it doesn't start at C. It doesn't start at A. F to E is a potential path because it ends at E, doesn't start at A, cost of 1. And then I also have A to E. But A to E has a cost of 7, and it is actually the starting vertex to the destination. So therefore, that one moves into the path list. Now I'm going to look at, for the next iteration, I need to get access to D and to F. Notice that after the second iteration, I have 1 more than I had before of possible paths, but I also have 2 more paths. Once I go into the path list, I never leave the path list. So in this case, you can see what's going to happen. So I have DE. How can I get to D? Well, I can get to D from B with a cost of? With a cost of? 2. Because I had D to E at 2, therefore B to E is 4. That means that B to D is going to be 2. Notice that I also have another path, DE, which is ADE, with a cost of
D to
Four.
E is 2 and
A to D is what?
4.
4.
4. So that moves directly into the path. So D to E, basically there's a B, DE. The B is added on, it's a potential path, but ADE is a path with a cost of 6. Now FE, notice that I have FE, so I can go CFE with a cost of 5, or I can go AFE, that's a path with a cost of 6. I can also go to F from E, which would be EFE. But because EFE has a cycle, that path, potential path, is removed. It's no longer a potential path, that path is a cycle. Once I have a cycle, I'm done. I remove the potential paths. So now I have 3 paths, and I have 2 potential paths left, and I'm going to look at all the places I can get to B and to C. Notice that to get to B, I do what? I can go from A to B with a cost of 1, making this a path, making this the 4th path. Now in terms of, I can get to C from F. But the problem with that, if I go from F to C, that creates a cycle, then this potential path is again removed from the potential paths. So that means I have no more potential paths. But I do have 4 solutions kept in sorted order, therefore the least cost path is A, B, D, E. A, B, D, E. So here's the cost of 5. Notice that there are actually 4 different ways to get there, but all of them are more expensive. This happened to be the longest path. But think about it. If I can go from A, if A to E was only a cost of, for example, 4, that would have gone right in here, and it would always stay at the top. It still would have been the best path.
At that time, that algorithm works.
Hmm?
If A to E cost is 4, then at that time, this whole algorithm works.
Yes. Yeah, the algorithm cannot stop until it exhausts all the possible paths. Once all the possible paths are either removed or moved into the path list, we continue. And then once they are gone, because at this point, at the very end, here's what we have. So we have nil here, and then the cheapest right here, that's our solution right here.
But if total cost of from A to E is 4, and
Is A to E is 5.
no, consider that from total cost from A to E is
If the cost, okay, so you're saying if this was only 4.
4, and
If this was only 4, then as soon as A to E was put into the possible path list, it would have gone here at 4. But it still would have had these paths in here. It's still possible that we could have had a longer path that was, for example, going from hop, hop, hop with a cost of 3.
Yep.
So we can't stop because we found a solution. This is a solution. I didn't know the 7 was going to be the worst solution.
No, but that post path list is like more than 4 then, and our path list is 4 at that time.
Here.
Like there is 4, and post pass list is more than 4.
I mean, if you can look, for example, here, notice that right now, when we stop here, if this one was 4, and this one is 4, then essentially you could stop here. Because you know that every partial path list is going to be at least 4. Or more than 4. The least one, if every edge cost is at least 1, and you have a 4 here, the cheapest you can get is 5, but you already may have a 4 solution, so you can stop. So you might be able to stop early if your potential paths are bigger than your already final path or minimum path so far. Yes, so there are some opportunities to stop early. Okay, any other questions or comments? Okay.
Is this also a BFS?
Well, you tell me what it is. Is it a BFS? Is it DFS? Or is it something different?
I think it's BFS.
Wait, first.
So we're starting here, and we're going 1, 1, 1, right? It's kind of a BFS, but it doesn't stop when you get to a path. So you have to complete the entire algorithm before you have a solution. Okay? Because the shortest path, you stop as soon as you visit the destination. But here you stop when you have no other potential paths that could be better. So it's kind of a depth again. That first. Okay. There's another algorithm that's very famous that basically gives you the same result. I'm not going to go through that algorithm. It's called Dijkstra's shortest path algorithm. You can take a look at it. I show you basically the same. I think this is a little bit different algorithm. But for example, you can try. What I would do if I were you, I would go through this example, maybe to see if you can use our previous algorithm to find out. You want to go from A to G, right? So where's G? G is right here. A is right over here. Notice that this is a directed graph or a non-directed graph? Non-directed graph, okay. So that means that the edges are, you can go both directions on the edges, okay? So you can see what is the cheapest. Do you think it's going to be 12? Hard to tell, right? Hard to tell. So go through this graph and see if you can go through the algorithm, see if you can find a solution for this one. Okay? So that's what I'm going to do right now with graphs. We're going to look at that. All right, so now what I want to do is I want to go back to our lecture Corman slides. Have we gone through the merge sort examples and the insertion sort examples earlier in the semester?
No.
We have not?
No.
Okay, good. I wasn't sure if we did. Remind me if I have. We didn't do insertion sort? The reason I'm asking is because I teach this course pretty much every semester. So sometimes I forget what it seems like. And you know, for you guys, a semester is a long time. For me, it's like semester. It's continuous. Okay. That's not the one I want. I want the one here. We want to go to lecture. Okay. Tell me if this is familiar. If this is familiar, then I'm gonna skip it. I don't think we have done it before yet. So what we're going to do is going to look at a bunch of different algorithms from our example. Have we done this or no?
No.
Okay. So first of all, we're going to be looking at a whole bunch of different sorting algorithms. Okay. And so the idea of a sorting algorithm is that we have a sequence, which means we have a set of values and they are in a particular order. And the order is very, very important because we want to sort them. So we want to go from this sequence of numbers to another permutation or arrangement of the same numbers, where basically the first number is less than or equal to the second, less than or equal to the third, so they are in what we would call non-increasing order. Non-decreasing order, rather. Non-decreasing order. So the numbers are either getting bigger or staying the same. So if the input is this one right here, notice that we have some violations. In fact, let me tell you about something interesting here that I'm going to come back to later on. This is not covered in these notes, but if you look over here, this is the correct sequence of sorting, right? Yes? So what we're going to look at is, let's look at the current sequence. Look where 8 should be. You see what I'm saying? 8 should be here. So if you look at 8 with respect to 9, they are okay. Am I right? 8 with respect to 9 is okay, correct? But notice that the numbers 2 and 4 and 3 and 6 should be to the left of 8. So therefore, we're going to call the incorrect ordering of 8 and 2 an inversion. Inversion. We're also going to call 8 to 4 an inversion, 8 to 3 and 8 to 6. So therefore, 8 has 4 inversions. Does that make sense? Does everybody understand what I mean by inversion? It is the incorrect ordering relative to the two numbers themselves. Okay, if we go to 2, know that 2 should be to the left of every single number. So we can say that 2 has an inversion with 8. 4 has an inversion with 4 has an inversion with 8. 9 has an inversion with 3 and 6. 3 has an inversion with 8, 4, and 9. And finally 6 has an inversion of 8 and 9. So we can count the number of inversions. Right? Let's count them again. So very quickly. So if we're looking at 8, how many inversions do we have with 8? 4, right? What are the numbers?
2, 4,
2, let's put them in order. 2,
4,
2, 3, 4,
2, 3, 4,
6.
6. Okay, let's go to, I'm going to put over here 2. What are the inversions with 2? 8. How about 3?
8 and 9. And 4.
8, 9,
And?
4.
4, 8, 9. How about 4?
8.
How about 5? There's no 5. Good. 6, we have a 6. So 6 inversions are
8 and 9.
8 and 9. 2, 3, 4, 5, 6. 1, 2, 3, 4. We have one more number. What is it?
9.
9. Okay. And 9 has an inversion of
3 and 6.
3 and 6. Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Is that right? 6, 7, 8, 9, 10, 11, 12, 13 inversions. We can consider the number of inversions as how close in order the numbers are in terms of being sorted. For example, if the numbers look like this, for instance, let's say I had 9, 2, 3, 4, 6, 8. I had this sequence. How many inversions with 9?
5.
5. How many inversions with 2? And just count, we can just count, okay. Well, you can count 2. How many inversions here? 1. So 1, 2, 3, 4, 5, 10. So 10 inversions. How many here? So we might be able to use inversions as a measure of how out of order an array is. And maybe how quickly we can sort it. Possibly an idea. Okay. All right, so we'll come back to the idea of inversion. So insertion sort. Okay, so we haven't done this before, right? Just want to make sure. Somehow I thought we had done it, but we have not. Okay. So insertion sort is this is the kind of sort it is. So the idea. How many people have heard of insertion sort? Okay, one person, two people. You've heard of it, but you don't count. All right, he's a cheater. All right, so what we have is we have some values. And so what we're going to do is we're going to do something like this. So we have the values in there, not in any order at all. They're all mixed up. So what we're going to do is we're going to take not the first element, but the second element out. And then we're going to look at the first element and say, is this element less than or equal to me? Because if this element is less than or equal to me, that relative to that element, I can just go back in, and we are going to be okay. Those first two elements are okay. You follow what I'm saying? So we take the second element out and look at the first element. Is it less than or equal to the second element? If it is, go back in. But if it's not less than or equal to, then it must be greater than. And if it's greater than, then it should be to my right. So I'll move the first into the second. then I'll have the first position open, but there's nothing else to compare it to, so I'll move this element from 2 into 1, and now they're okay. So we're going to insert the element that we took out into the correct location relative to the elements that we've considered so far. Okay. So now what we're going to do is we're going to take the third element out. When we take the third element out, what about the first two elements? They're in order. So now, if I take this element out, I will say, is the second element less than or equal to? Because if the answer is yes, then I know that this element is also okay with respect to that one. I can just put it back to number 3, and we have 3 elements in order. So then I can go to the fourth element. When I take the fourth element out, the first 3 are okay. I take the fourth element out, and if this element is less than or equal to, I'm good. But if it's not, I slide it. And then I look at the second one. Are you less than or equal to me? If the answer is yes, then I can go into this slot, because then everything is going to be fine. Because I slide only if the element is greater than me. So if the fourth element is greater than me, it slides. But if this element in position 2 is not greater than me, then I should be in that position. So every time I do a J iteration, and the J iteration is out here, this is the outer loop, this is the inner loop. Every time I do a J iteration, I take the element out, put it into some key value, and then I'm going to look at I equal to J minus 1. So if J, for example, is equal to 10, then I take the 10th element out, and then I goes from 9, decreasing, while I is greater than 0, and AI is greater than key. Slide, and move I. But once it's no longer greater than the key, then drop the key into AI plus 1. And that's how we do insertion sort. Now, we did talk earlier about bubble sort. So now we can talk about insertion sort. We talked about bubble sort, and we said that the complexity of bubble sort basically was n squared, theta n squared. But we also looked at a way to compare how many passes we need in bubble sort. So if we never did a swap in bubble sort, we could stop the passes. But we said it's very difficult to tell whether that's actually a better algorithm on average without really knowing what average is and how to compute the average. The consensus is that it's a very bad algorithm, even with that improvement. It's still not a good algorithm. Unless you happen to know that 99% of the time, your data only needs one pass. Then it's a great algorithm. But if you have random data, it's a terrible algorithm. You'll end up doing at least as much work or more trying to stop early and then not being able to stop early in terms of the number of passes. But insertion sort, let's compare that. So we know the worst case of bubble sort is theta n squared. What is the worst case of insertion sort? What is the worst case of insertion sort? Well, let's find out what the heck is a worst case anyway. The worst case would occur when I take an element out from the position J into key, and every time I take it out, I have to slide every single element until I get to position 1, I put it in there. When I take the next element out, I got to do it again. Now, can that actually happen? Can that actually happen? Let's see. Let's pretend we put some elements in. We're starting with a very small array, size 3, n equal to 3. So our elements are going, we know that if we put the elements in order of 1, 2, 3, we're going to take the 2 out, we're going to put it back in. We're going to take the 3 out, we're going to put it back in, and we're done. What if we put them in the order of not 1, 2, 3, but 3, 2, 1? So when I take 3, 2, 1, I take the 2, I have to slide the 3, put the 2 in. So now I have 2, 3. What's over here? 1. So I got to slide the 3, slide the 2, slide the 1. That appears to be the worst case. So what's the worst case for insertion sort? What's the worst case in terms of the order of the data? It's in reverse sorted order. Starts from the biggest to the smallest. That appears to give us the worst case. Okay? What about the best case? The best case is, well, let's try it if it's sorted. If it's sorted, we take the second element,
Go back.
third, fourth, fifth. How many times do we touch each element?
One time.
One time. So basically it's going to be, so the best case is theta n. What's the best case of bubble sort?
1.
1 is not a good answer.
Yeah.
Also theta n. They actually have the same best case. Remember I told you in bubble sort, if you remember bubble sort, is if we're going to, I think we're comparing going downward like this. So if we have the smallest element at the bottom, but everything else is perfect, what's going to happen is like perfect, 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 bloop. It's one move. Perfect, 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 bloop, perfect. And so we're going to require n-1 swaps just because that little tiny element is going to take it n-1 comparisons to get up to the top. But the number of inversions doesn't seem like it's going to be very bad. Because the only element that really has inversions is the one element. And you can count inversions two different ways. You can say if 5 has an inversion of 6, then 6 has an inversion of 5. That's why I think we get something wrong here, because I think we need to have an even number of inversions. But we have to go back and check it out what we did wrong. So we have to have an even number of inversions. So if we count inversions, so for example, if I find that 2 has an inversion with 9, I'm not going to count 9 having an inversion with 2. My inversions are going to be always in one direction, which makes sense. So therefore, if you have n elements, and only one of them is out of order in terms of inversions, like the smallest element at the bottom, but everything else is perfect, you have effectively n-1 inversions. What's the maximum number of inversions you can have? Well, think about 4 elements in reverse order. So 4 is going to have how many inversions?
3,
3?
2, 1, 0.
Okay. So what is that going to be, theta?
n-1 factorial?
No, not so high. What's going to be the worst case of inversions? So imagine I have 100 numbers, but they're sorted from 100 down to 1. So 100 should be over here. So it's got 99 inversions. This one's got 98 inversions, 97, 96, 95, right? So how many inversions are we going to have for theta?
Sum of n into n plus 1 by 2.
N squared. I think you said it back there and you said it here. So it's going to be theta n squared inversions. So the worst case is going to be n squared. That's about the worst you can do in terms of inversions. What about best case? Well, best case could be 0. If it's sorted, there are no inversions. And of course, could you have one inversion? Yeah, you could have one inversion. If everything is perfect except the first 2 elements are reversed, then you can have 1 as an inversion of 2, but you don't count 2 with 1 because you're only going this direction. So you can say it's 1 inversion. So but this element that I gave you down here being only 1 out of place, that gives you n inversions. But certainly n is a lot less than n squared inversions, which would be the worst case. So you can sort of see how you can do these inversions. Okay, so let's talk about what would happen to this same situation where you had 1 element out of place. So let's look at insertion sort. So what we have is, we have the biggest element is here. The biggest element is here. But then we have the smallest and everything is perfect. So it starts with the smallest element after the biggest, then it goes all the way up to the second biggest element. So what's going to happen, we take this element out, and what do?
Compare to the left.
Next
What do?
Compare.
Do we slide or not slide?
slide.
Do we slide or not slide? We slide, because we're going to take the smallest element out, we're going to slide, put the smallest element where it's supposed to be. Now I'm going to go to the third element. What am I going to do? Slide, and then I'm going to compare. Do I slide again?
Yeah.
No,
Two
because remember, it's biggest element and then
smallest.
in order. So once I go to the third element,
Already.
I slide the biggest, but the smallest one is before this one, so I go in here. So how many times am I going to slide? Sliding is the complexity.
N-1.
Okay, so therefore, in the same, but for the same algorithm, bubble sort could be as much as n squared. It turns out that these two algorithms have a lot in common, but they also have a lot that is different. One of the things they have in common, they have the same worst case, theta n squared. One of the things that they have in common, they have the same best case, theta n. But the difference between insertion sort and bubble sort is that nobody uses bubble sort for anything except to teach you what sorting is all about without giving you a headache. And insertion sort is actually used in professional algorithm implementations to enhance the performance of high-performing sorting algorithms when they get closer to finishing. They actually switch from one algorithm and they switch into insertion mode. Because it turns out for small problems, insertion sort is actually very, very efficient. Much more efficient than even high-performing, high-end algorithms like quicksort or merge sort. They're actually just better than those. And we'll talk about those types of, why that even would be the case, or et cetera, et cetera. Okay. All right, so you see what this is going to look like, and I already kind of showed you this, so you see what's going to happen here. We take this 2 element out, and what's going to happen, 8's going to slide, right? Now we're going to take the 4 out, and 8's going to slide. Now we're going to take the 9 out, and it's going to go right back in where it was. Now we're going to take the 3 out, 9's going to slide, 8's going to slide, 4's going to slide. See what's going to slide? These are slide, 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 and 3 is going to go here. We're going to take the 6 out, and we're going to slide with 9 and 8. And that's it. Now we're done. So that's insertion sort. All right. We talked a little bit about worst case, average case, best case. You know what bogus means? Not realistic, useless, stupid. That's what bogus really means, right? Worst case, usually. Average case, sometimes. And best case, bogus. Best case is having a best case attitude is very positive but not realistic. It's like buying one lottery ticket for the mega bucks and expecting to win. It's nice. It's very good until they pull the numbers and you realize, okay, you've lost again. Okay, so it's nice that the best case is everybody buys lottery tickets because they think it's going to be the best case. But really, 0.999999999 out of them are losers. Week after week after week after week after week. Of course, if somebody does win, and when they show you a picture of that one person, you automatically imagine that's going to be you next week. But in practice, it's never going to be you. It's going to be that one person, in some faraway state that's going to win every once in a while. They didn't expect to win either. Okay. We talked about theta notation, blah, blah, blah. Okay. So insertion sort analysis. We talked about this. If the input is reverse sorted, then what we get is the number of slides is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll add all those numbers together. And of course, that's going to be n times n plus 1 over 2, which is n squared minus n over 2. So therefore, it's going to be theta of n squared. Average case, all permutations equally likely. It's still going to be theta n squared. So is insertion sort a fast sorting algorithm? And the answer is moderately so for small n, not at all for large n. So it's kind of a mixed bag. So it's not a great algorithm on its own, but it does work nicely for smaller values. For small values, it tends to perform well. Okay, how many of you are familiar with merge sort? Yes?
How do we decide which set is large and small? when you use insertion sorters?
30 is small. More than 30 is large.
What is that?
And that comes from statistics, by the way. So, roughly speaking, small, I'm talking, when I say small, I mean really small. 30, I'm not joking. 30. You want to make it 32? Okay. You want to make it 1,000? No. So usually when we're talking about small, we're talking about around 30, which is sort of statistical breakdown between a small and then bigger type data. Okay. How many people have heard of merge sort? Okay, the idea of merge sort is like this. It can be a recursive algorithm, it can be an iterative algorithm. And so we want to merge sort elements 1 through n on some array. If n is equal to 1, if the array only has one element, then we're done. Sorting an array of one element is done. Okay. But if n is some bigger number, then what we're going to do is we're going to sort from 1 to the middle, n over 2 ceiling, and n over 2 ceiling plus 1 to n. So we're going to split it into two as close as possible pieces. If it's even, we can split it exactly in the middle. If it's odd, we need to take one more on one side. And then, after recursively sorting the left and the right half, we merge the two sorted lists. So we're going to look at something like this. So this is the first list. This is the second list. So now we're just going to talk about merging it. So this is the merging part of it. So we want to, these two lists are already sorted. So this is, we're assuming that we have recursively sorted the first list and the second list. And now here comes the merge. So the key routine is merge, and we're going to compare 2 against 1. 1 is smaller, so we take it. Okay, and then we have 2 and 9, so we're going to take 2. Okay, so now we got what? 7. So we have 7 and 9, right, left, because we took these ones here, so we have 7 and 9. And we're going to take 7. And now we have 9 and 13, so we're going to take 9. Now we have 11 and 13, so we're going to take 11. Now we have 13 and 12, we're going to take 12. Now we're out of data on the right side, we just take 13 and 20. Because we've got nothing else to take, so we'll take 13 and 20. So the time, notice that it's basically theta n to merge. Theta n to merge. Why n? Well, basically, it's 8 elements, right? So you're doing comparison, take 1. 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 So roughly speaking, you can expect to have, roughly speaking, how many comparisons? In the worst case, about n comparisons. How about in the best case?
No comparisons.
Got to have some comparisons. The best case, probably n over 2. For example, imagine that this list here was 2, 7, 13, 20, and this list was 25, 26, 28, 37. You see what's happened? Compare, take, compare, take, compare, take, compare, take, out of elements. Take, 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 take. So we only need 4 comparisons. So the best case is roughly n over 2 comparisons, which is theta n. The worst case, about n comparisons, which is also theta n. So the time complexity to do the merge is theta n. So the merge sort works like this. So to merge sort the array elements from 1 to n, if n is 1, we're done, and that means we are done, and that's the base case. It's the basis of the recursion. Otherwise, we will recursively call merge sort on the left half, and then we will also recursively call this from the... So you can see what's going to happen here is the amount of work being done. If you look at the algorithm, with respect to how the master algorithm described the work, coming into the array is an amount of size n. Okay? And what we're going to do is this level 0 of the recursion is going to recursively send half and recursively send the other half. Does that look familiar? Okay. Now what does this n represent at level 0? No. What does n represent? It's the actual work. But what is the actual work at level 0?
Merging.
Merging! Okay, and we just looked at the merging, right? So basically, so level 0 takes n elements. It recursively sends in two halves. Eventually they do their thing, and we come back up here, and now we have two sorted halves. I have to merge them. That's the work. Okay, so now level 1 gets n over 2. It then will generate these deeper levels of t of n over 4, t of n over 4, right? They will merge them, and this will basically now merge them, but the problem size going into level 1 was n over 2, therefore the merging cost will be
N over 2.
n over 2. It will be the same here, and it will be the same here, n over 2. And you can imagine what's it going to be here.
N over 4.
So what's going to happen is the cost at level 2 is going to be n over 4. This is the actual work. And of course the same thing is happening on that side, right, of the recursion tree. And of course what's going on is this tree is growing very, very balanced. It's a very balanced tree. Eventually it's going to go to unity. How quickly it's going to go to unity? Well, it's dividing the size of the data in half. So you can only do that log 2n times, which means that the height of the tree will be log raised 2 of n. And the amount of work being done at each level is going to be n, 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 n. So the algorithm will be theta n log n. If we look at it from the standpoint of writing the algorithmic complexity, then the t of n based upon this algorithm is going to be t of n. It's a very bad pen. I need to refresh my pens. I have more pens here. Other than so we have t. Try again. T, perfect, of n is equal to, that's t of n over 2, t of n over 2. So it's going to be is equal to 2t of n over 2 plus the cost of the merge. This fits into nicely into our master algorithm where f of n is equal to n, and n to the log b of a is equal to n to the log 2 of 2, which is going to be n. So they're both the same. So we have the case where n is equal to n log to the 0 power of n, with k equal to 0. So therefore our algorithm theta will be theta n log n. And you can see here that the work is the same everywhere, and the number of levels is log to n, and that's where we're going to come up with that result for this one. Okay, and you can see again, this is 2t of n over 2. Let's see n is just a constant, right? 2n, 3n, whatever, just some n value. And so we've seen this before. Very simple. And so that's the height, that's the work, that's the work. The work is the same. And so that's what we have here. So the whole thing is going to be NLGN.
Professor, is the k value 0 or 1?
K value is 0 here. It ends up being 1 here in the theta.
Something power 0 is 1. So k value should be 1, I guess.
This is log to power 0 of n is 1. That's why n is equal to n. So we have to set f of n equal to n log b of a, including a log of n to the k power. So the only way we can make them equal is when k is equal to 0. See what I mean? They're equal to each other, right? I can't skip it. I can't just say they're equal to each other. I need the log in here. So the only log that makes it, if the log of n is equal to 1, that only happens when the power is 0. So that's why k is equal to 0. And then in a theta solution, the k is going to go immediately to 1 higher than the k value in the equality. Okay. In practice, merge sort beats insertion sort for n greater than or 30. I'm not kidding about that. Statistically, 30 is a very important number. You guys ever take statistics? Some, maybe. Nobody took statistics? You took statistics.
Yes.
Yeah, so basically when you're talking about sample sizes, when you're looking at numbers that are under 30, they tend to be not representative of the population. They tend to start approximating the size, the behavior of the population after 30. Well, data of size 30 tends to run at higher complexity. It starts getting, so that the worst case really starts adding up. Okay? 30 squared is what? Is 900. Right? But 3,000 squared is 9 million. That's a big difference in operation. So when you're talking about 30 squared being 900, a computer can execute something on the order of 900 very, very quickly, but when you get to 9 million, it gets very, very slow. Now you say, well, wouldn't more efficient algorithms do even better than 900? The answer is some of the most efficient algorithms have a lot of overhead, including merge sort has a lot of overhead. We didn't talk about it, how to implement merge sort and why it's such a costly algorithm for small problems. It's like when you want to solve a small problem, sometimes you do it more manually. When you want to do a large problem, you do it more systematically. You can buy, if you want to build a big house, you can buy big tools, expensive tools, because you're going to make so much money from when the house is sold. When you have a very small job, and you make a small amount of money on that job, you can't afford to buy the expensive tools because then you will make no money on the job. It's a strange comparison, but there's a big truth in there. So the more benefit you're going to get, the more you can invest into it. The less you can invest into it. Okay, so we'll continue with these slides, and I'll do a little bit more from the book on. Well, actually, on Thursday you're going to be on Wednesday.
Wednesday, okay.
We might go over you guys got the homework in? Homework is done? Okay. So we may go over the homework on Wednesday, or we may continue with the notes, so we'll have to see what we're going to do. Okay, I'll see you guys.